Now, let us learn about the pseudo forces and non-inertial frames. The non-inertial frames, the reference frames in which Newton's second law does not hold, are called non-inertial frames or accelerated frames. Any frame of reference in which is accelerating or which is not moving with constant velocity or which is not at rest is called the non-inertial reference frame. The inertial reference frames, these are the frames in which Newton's law hold, are called inertial frames. The inertial frames are non-accelerated forms. For example, any person is at rest and that person is moving an object. Then, with respect to this object, the acceleration of the person is 0. As the acceleration of observer is 0, then this person is in non-inertial frame. If this observer is inside a bus moving with some acceleration 10 meters per second square, then this person is accelerating with respect to time, so this observer is in non-inertial frame. Now, whenever we are dealing with the non-inertial frame, to apply the Newton's laws in non-inertial frame, we have to apply some pseudo force. So let us understand what is pseudo force. A pseudo force is a fictitious force which is introduced in the non-inertial frames to make the Newton's law valid. Remember, it is a fictitious force. It is not acting actually on the object or on the system. We are assuming to be acting it on the system so that we can apply Newton's law in the given system. Now, how will you calculate these pseudo forces, or how will you translate the non-inertial frame into inertial frame? For example, there is one non-inertial frame which is moving in this direction with acceleration a0. This object is moving with acceleration a0, and this frame of reference is moving with acceleration a. That means the force on this reference frame is Fr. If we apply same amount of force on the object in the opposite direction, then this object will be no longer in the accelerating reference frame. So it will be now in the non-inertial frame. So we have to apply the opposite acceleration to translate non-inertial frame into inertial frame. So let us consider a particle of mass m being observed from frame of reference y, that is capital Y, and small y. Y is the inertial frame of reference, and small y is the having acceleration a with respect to capital Y, that is, it is the non-inertial frame of reference. Now let Fr be the real force acting on the particle and Fp vector be required a pseudo force to make the Newton's law valid in the non-inertial frame. That means Fr is the real force and Fp is the pseudo force, it is the fictitious force. A naught is the acceleration of mass m with respect to the inertial frame of reference y. So, the real force is ma naught. Fr plus Fp is equals to ma naught minus ma, as it is acting in the opposite direction. Now subtracting both the equation, we will get Fp is equals to ma. So Fp should be equal to minus ma. The negative sign shows the opposite direction of A. Here note that the direction of pseudo force is opposite to the acceleration of the observation frame, and the magnitude of pseudo force, the direction is opposite to the acceleration of observation frame, and the magnitude of pseudo force is mass of the observed objects times the acceleration of the observer variation frame. So pseudo force is equals to mass of the observer into acceleration of the reference frame. Now let us see moving elevator problems based on the application of pseudo forces. Here a person of mass m is standing on a weighing machine inside an elevator. We want to find the weight reading by the scale in different situations. Here note that the weighing machine will measure the normal reaction applied by it. The first case is lift or elevator is at rest. If lift is at rest, then the man will be applying force in downward direction, that is equal to mg, and the same normal reaction will be applied by the scale on the man in upward direction. So the reading of the weighing machine will be exactly equal to mg. Now let us take case 2. In this case, this lift is accelerating upward with acceleration a1. It is accelerating upward with acceleration a1. Now, as the lift is accelerating, it is non-inertial frame of reference. To make it inertial frame of reference, we will apply same acceleration in the opposite direction. That means we have to apply the acceleration a1 in the downward direction. So for the man, the net force or net acceleration in downward direction will be g and a1. So the weight of the person will be equal to m into g plus a1. This will be the normal reaction applied by the weighing scale. Now let us see the third case. In this case, the lift is accelerating downward with acceleration a2. So this is accelerating downward with acceleration a2. Again, this is non-inertial frame of reference as it is accelerating in downward direction. to make it inertial frame of reference, we have to make the acceleration equal to 0. So let us apply same amount of acceleration, that is a2, in the opposite direction. Now the forces or acceleration of the person will be g in downward direction and a2 in upward direction. So the weight of the person measured, or the normal reaction applied by the weighing scale, will be m into g minus a2. So in this case, weight is reduced. And in this case, weight is increased. In the case 4, the lift is moving up or down with constant velocity. As it is moving with constant velocity, the external acceleration or of reference frame is 0. So it is inertial frame of reference. So we do not need to apply any pseudo forces. So in this case, weight will be same as mg. So this is the case when it is accelerating upward, and this is the case when it is accelerating downwards. Now, in the 5th case, the lift is retarding upward with acceleration a3. The lift is retarding upwards, that means the motion is in upward direction, but as it is moving upward and retarding, the retardation will be in downward direction, the acceleration will be in downward direction. So it is basically moving with acceleration a3 in downward direction. So to convert it into inertial frame of reference, we have to apply same amount of acceleration in the opposite direction. So in this case, the reading of the weighing machine will be m into g. This acceleration is acting in upward direction, so g minus a3. Now the case 6. In this case, lift is retarding downward with acceleration a4. Now it is moving in downward direction, but it is retarding, so acceleration will be in the opposite direction of motion. So acceleration is in upward direction a4. Again, to convert it into inertial frame of reference, we have to apply the acceleration in the opposite direction, that is a4 in downward direction. So in this case, the weight will be equal to m into g plus this additional acceleration a4. Now we have seen that when lift is accelerating downwards with acceleration a, the weight will be mg minus e. Now, if lift is free falling, then its acceleration will be equal to gravitational acceleration. So in this case, the weight will be m into g minus g, that will be equal to 0. So this will be the condition of weightlessness. So during the free fall of lift, the weight of the person will be 0. Now, let us see the system of pulley kept inside an elevator. This is an elevator. From the upper fixed surface, one pulley is hanged, having two blocks M1 and M2 passed over the pulley with the help of a massless string. For this case, if this lift is at rest, we have seen the value of acceleration as m1 minus m2 into g upon m1 plus m2. The tension force in this string is 2 m1 m2 upon m1 plus m2 into g, and the force acting at this point will be equal to 2t, that is equal to 4 m1 m2 upon m1 plus m2 into g. Now let us consider again the cases of acceleration one by one. The case 1 is the lift is accelerating up with acceleration a1. If the lift is accelerating up with acceleration a1, then we want to find the acceleration, tension and force with respect to pulley. Now, with respect to pulley means, let us say one person is standing or sitting on this pulley. That person is also moving up with acceleration a1 with this elevator. So in this case, our observer is in accelerating frame. So this is the non-inertial frame of reference. To convert it into inertial frame of reference, we have to make this person to have zero acceleration. To have zero acceleration, we have to apply the acceleration a1, the same amount of acceleration a1 in the opposite direction. So in this case, the net acceleration will be g and a1 in the downward direction. So the acceleration of the block with respect to pulley will be m1 minus m2 upon m1 plus m2 into g plus a, because the net acceleration in downward direction is increased, that is g plus a1. The tension force will be 2 m1 m2 upon m1 plus m2 into g plus a1, and the force will also be 4 m1 m2 upon m1 plus m2 into g plus a1. Now let us take the another case in which a lift is accelerating down with acceleration a2. Now again let us take the observer at the pulley. This whole system is accelerating downward with acceleration a2. So our observer is also accelerating. To make his acceleration 0, we have to apply same amount of acceleration in the opposite direction. So let us apply a2 in the opposite direction. So in this case, G is acting in downward direction and a2 is acting in upward direction. So the acceleration of blocks with respect to the person sitting on pulley or with respect to the pulley will be m1 minus m2 upon m1 plus m2 into, in this case the accelerations are subtracted, so G minus e2. The tension force will be 2 m1 m2 upon m1 plus m2 into G minus a2, and the force will be 2T, that is equal to 4 m1 m2 upon m1 plus m2 into G minus e2. Now let us see some examples based on the pseudo force. These are the most frequently asked type questions. The first question is, a man is standing in an elevator which is moving upwards with an acceleration a. Make equation for the Newton's law in the ground frame as well as lift frame and show that they are equivalent. Now first we want to make the equation in the ground frame. So for the ground frame, the force acting will be normal reaction in upward direction and mg in downward direction. As the result of these two forces, this person is moving up in upward direction. So n minus mg is equals to ma. So normal reaction will be equal to mg plus ma. This is in the ground frame. Now in the lift frame, the lift frame is accelerating frame, so we have to apply one pseudo force. As it is accelerating in upward direction, we will apply pseudo force in downward direction. So normal reaction will be mg plus the pseudo force, and we know the pseudo force is given by mass times the acceleration of the frame. Here the acceleration of the frame is a, so n will be equal to mg plus ma in that case also. So with reference to lift or with reference to ground, the normal reaction will be same, that is equals to mg plus ma. These two equations are same because we have converted this non-inertial frame of reference into inertial frame of reference. Now let us see another example. A railroad car is accelerated with an acceleration a. What will be the angle made by the pendulum bob? You want to find the angle made by the pendulum bob hanging inside a car. Analyze the problem from ground frame as well as from the car frame. Let's say this was the initial situation of the pendulum. Now as car is accelerated in right direction, the bob will move in left direction, and let's say it is making an angle theta with the vertical. If we draw the free body diagram of this bob, then on this bob, the force acting is mg in downward direction, and in this direction the tension force will act. This angle will be theta, as it is making an angle theta with vertical. So this component will be t cos theta and this component will be t sin theta. So with respect to ground frame, this is with respect to ground frame, t sin theta is equals to ma. This stretching of the pendulum or bob is due to the acceleration a. So t sin theta is equals to ma. And t cos theta is equals to mg. Taking the ratio, this t will get cancelled out and this m will also get cancelled out. So tan theta will be equal to a by g. Now, if we see with respect to car frame, the car frame is non-inertial frame of reference. To see with respect to car frame, let us say one person or one observer is standing inside the car. So the observer is also accelerating with this car. That means this observer is non-inertial. To make him inertial, we have to apply same amount of force in the opposite direction. So this opposite direction force is ma, the downward direction gravitational force mg, tension T. Divide this tension into components. This will be t cos theta and this will be t sin theta. As under the action of, so in this case this t cos theta and mg are balanced. So t cos theta is equals to mg and this t sin theta is balanced by ma. So t sin theta will be equal to ma. Again taking the ratio, that is sin theta upon cos theta will be equal to a by g. So with respect to both the observer, one is at rest on the ground and another is inside the accelerating frame, we are getting same value of angle, that is tan theta is equals to a upon g. Now in this question, for the shown system, find the range of acceleration for which the block does not slip relative to the wedge. Here a wedge of mass, let's say small m, of angle of inclination theta is kept on a surface. Let's say the surface is smooth. Now this object of mass capital M is placed on the wedge. The coefficient of friction between these two surfaces is mu. Now this wedge is given some horizontal acceleration. So this wedge will start moving in this direction. But it is given that the block does not slip relative to the wedge. So even if the wedge is at this position after some time, the block should be at the same position only. So let us assume that one observer is sitting at the top of the wedge. With respect to this observer, this block should not slide. So it should not have any motion along the plane. That means the forces along the plane must be balanced. So this is the key concept to solve this problem. So first we have to draw the free body diagram of block, but not with respect to ground. Here we are seeing it from the top of the wedge. So the FBD should be with respect to the wedge. So this is the block. The gravitational force in the downward direction is mg dividing this force into components, along the plane component will be mg sine theta and perpendicular to the plane component will be equal to mg cos theta. Now, as acceleration is acting in this direction, actual acceleration is in this direction, we have to apply a pseudo force because we are viewing it from the wedge, which is non-inertial frame of reference. So to keep this person at rest, we have to apply the force in opposite direction, that is equal to ma. So let us divide this pseudo force into two components. One is along the plane and another is perpendicular to the plane. So this component will be ma cos theta and the perpendicular component will be ma sin theta. The force will act in the opposite direction of mg sin theta, that is the frictional force mu n. So if we show the forces on the axis, in the downward direction force will act, that is mg. The component along the plane will be mg sin theta and the component perpendicular to the plane will be equal to mg cos theta. In this direction, along the plane in upward direction, a frictional force will act, that is equal to mu n. Now, as block is accelerating in this direction, we have to apply pseudo force in opposite direction, that is Fp is equals to m into a. So let us divide this ma into two components. So this component will be ma cos theta and this component will be ma sin theta. Now, we do not want any motion along this plane, so the forces should be balanced. That means the downward force mg sin theta should be equal to the upward force mu n plus ma cos theta. So mg sin theta is equals to mu n plus ma cos theta. So mg sin theta minus mu n is equals to ma cos theta. But the normal reaction here is mg cos theta plus ma sin theta. This is the normal reaction. So mg sin theta minus mu into mg cos theta plus ma sin theta is equals to ma cos theta. This m will get cancelled out. So g sin theta minus mu g cos theta minus mu a sin theta is equals to a cos theta. So g sin theta minus mu g cos theta is equals to a cos theta plus mu a sin theta. From this we can write acceleration is equals to g sin theta minus mu g cos theta divided by cos theta plus mu sin theta. Divide all the terms with cos theta, then we will get a is equals to g tan theta minus mu divided by 1 plus mu tan theta. This is the value of minimum acceleration. And the maximum acceleration will be 1 plus mu plus tan theta divided by 1 minus mu tan theta. The acceleration is maximum, that means the mu n will be negative. So this is the range of acceleration for which the block will not slide along the plane. Now let us see another example. Here there is a block. There are two blocks of mass m connected with a massless string, and this string is passing over this pulley. The coefficient of friction at both the surfaces is mu. This block has applied this acceleration A. We want to find the range for which the system remains in equilibrium. The system remains in equilibrium, that means this block does not slide in downward direction and this block does not move horizontal. So let us draw the free body diagram of this block. This block is M, and on it the downward direction force mg is acting. The tension force is acting in upward direction. It tries to move in downward direction. Frictional force will act in downward direction. This block will apply the normal reaction and the pseudo force is applied in the opposite direction. If this is the acceleration actually produced, then pseudo force will be in opposite direction, and pseudo force will be mass times the acceleration of inertial frame. So for maximum value of acceleration, the tension is equal to mg plus mu n, and the normal reaction is balanced by ma. So normal reaction is equals to ma. The tension force will be mg plus mu into normal reaction is ma. So the maximum acceleration is given by, from this two we can write A max is equals to T minus mg upon mu into m. Solving these two equations, we have n is equals to ma and T minus mg is equals to mu m e. So we will get E is equals to T minus mg upon mu into m, and the minimum force will be mg minus T upon mu into m. Now let us see some previous year questions. A block of mass m is in contact with cart C as shown. The coefficient of static friction is mu. The acceleration alpha of the cart that will prevent the block from the falling is. Here in this case, this block should not slide down with respect to this cart. This cart is accelerating, so it is the non-inertial frame. For that we have to apply the pseudo force on this object. So if we draw the free body diagram of block M, then in the downward direction force mg will act. Due to that, in the upward direction frictional force will act, that is equal to normal reaction. The cart is accelerating in this direction, so the pseudo force is applied in this direction, that is m alpha. So the block will apply the force of m alpha on the wall of cart. So wall will also apply some normal reaction. From this we can write normal reaction is equals to m alpha. Now the condition for the block not to slide is that mg, the downward direction force, should be less than or equal to the frictional force, that is mu n. From this we can write mu n should be greater than or equal to mg, but normal reaction is m into alpha. So mu into m alpha should be greater than or equal to mg. This m and m will get cancelled out. So mu alpha should be greater than or equal to g. We want to find the value of alpha. So alpha should be greater than or equal to g by mu. The minimum value of alpha is g by mu. So this will be our answer. Now let us see one example based on circular motion. The two stones of mass m and 2m are whirled in horizontal circles. That means the gravitational force at each of the point is same. The masses are m and 2m. The heavier one in radius r by 2. So the radius of heavier one is r by 2 and the lighter one in radius r. The tangential speed of lighter stone is n times that of heavier stone when they experience same centripetal force. The centripetal force acting on them is same. We want to find the value of n. Two masses are revolving in two different circles. One is of radius r by 2. The heavier one in radius r by 2. So the mass m2m will revolve in circle of radius r by 2. And the lighter one in radius r. Now it is given that the tangential speed of lighter stone is n times the heavier stone. Let's say the tangential speed of heavier stone 2m is v. So the tangential speed of the lighter stone will be n times v. It is given that they are experiencing same centripetal force. So we can write F1 is equals to F2. Centripetal force is given by mv square by r. For this case, the mass is 2m into speed is v. So v square divided by r. R is the radius. Here radius is r by 2 is equals to mass into velocities and v whole square divided by the radius is r. So 4m v square divided by r will be equal to n square mv divided by r. This m, v square and r will get cancelled out. So we will find n square is equals to 4. So n is equal to 2. So this is our answer. Now a question based on conservation of linear momentum or the impulse. A rigid ball of mass m strikes a rigid wall at 60 degree as shown in the figure. The ball of mass m is striking the wall at an angle of 60 degree with horizontal. It returns with same speed v at an same angle 60 degrees. We want to find the value of impulse imparted on the wall. Here the definition of impulse is F is equals to F into T, or impulse is equals to change in linear momentum. Here the appropriate formula will be change in linear momentum. So simply impulse is final momentum minus initial momentum. For that we have to divide this velocity component into two parts. This component of final velocity is divided into two horizontal and vertical parts. This angle is 60 degree. So this component will be V cos 60 degree and this component will be V sin 60 degree. Same way, dividing the initial velocity in this way, this angle will be 60 degree. So horizontal component will be V cos 60 degree and vertical component will be V sin 60 degree. So the initial velocity is given by taking this direction as positive, this as negative, upward as positive and downward as negative. The initial velocity can be written as V cos 60 degree I cap minus V sin 60 degree j cap. Same way, the final velocity V will be this V cos 60 degree is in along the negative x direction, so minus V cos 60 degree I cap minus V sin 60 degree j cap. The impulse is change in linear momentum, that is mass into final velocity minus initial velocity. So I will be equal to m minus V cos 60 is 1 by 2 I cap minus V sin 60 is root 3 by 2 j cap minus V cos 60, that is V by 2 I cap. This minus in this minus will be plus V sin 60 is root 3 by 2 j cap. This minus V root 3 by 2 j cap and plus V root 3 by 2 j cap will get cancelled out. So I will be equal to m into minus V by 2 into 2. So I will be equal to mv. Here important point is the component along the wall will remain same. Now in this question, a plank with a box on it at one end is gradually raised about the corner or about the other end. As the angle of inclination with horizontal reaches the 30 degree, the box starts to slip and slides 4 meters down the plank in 4 seconds. What are the coefficients of static and kinetic friction? Here, the maximum angle possible for this inclination is 30 degree on which this block will be at rest. As we increase the angle just from 30 degree, the block will start sliding. So the angle of repose for this block and wedge system is 30 degree. We know that angle of repose tan theta is equals to mu s. So tan 30 degree will be equal to mu s. So mu s is approximately equal to 0.6. That is, coefficient of static friction is approximately 0.6. Now once the block starts sliding, it is traveling a displacement of 4 meters along the plank in 4 seconds. So the displacement is 4 meters and time is 4 seconds. We want to find the coefficient of kinetic friction. While the block is sliding down, the forces acting on it will be G mg sine theta in downward direction, and the frictional force in the upward direction, that is equals to mu n. Here the normal reaction is mg cos theta. So the net force in downward direction will be mg sine theta minus frictional force, that will be mu mg cos theta. As this block is moving, this will be coefficient of kinetic friction. So the net acceleration will be g sine theta minus mu k g cos theta. Now, from this data, we can find the acceleration by using the Newton's second law of motion. S is equals to ut plus half at square. So displacement is 4. Initially it was at rest, so u is 0 plus half into acceleration, and time is 4 square. So acceleration will be 8 by 16, that will be equal to 0.5. So acceleration is 0.5 is equals to, g is common, it is 10, into sine theta, the angle is 30 degree, so that will be 1 by 2 minus mu g cos theta, this cos theta will be root 3 by 2. So 0.5 will be taking this half common, 5 into 1 minus root 3 mu. So 0.1 will be equal to 1 minus root 3 mu. This is mu k. So root 3 mu will be equal to 1 minus 0.1, that is equal to 0.9. So root 3 mu is equals to 0.9. Mu will be equal to 0.9 divided by root 3. So mu will be approximately 0.5. So the coefficient of static friction is 0.6 and coefficient of kinetic friction is 0.5. That is all for today. Keep practicing. Thank you.